So 2.5 is on exploring graphs of rational functions. We have three key points to note when we are looking at graphs or exploring graphs of rational functions. The first thing is what is the vertical asymptote, if there is any, or VA for short. The second thing is there a horizontal asymptote? Or HA for short. And the third thing is, are there any holes in the graph? And the holes in the graph are basically discontinuities that happen. They're continuities. They're like point discontinuities that we'll see. Okay. So for example, if I were to consider a function like this, f of x equals 1 over x minus 1, you can see this is a transformation of the reciprocal function shifted 1 unit to the right. So if you were to graph this, you could tell that in a rough sketch of this graph, you would have something that looks like this. You'd have a the new vertical asymptote would be here, and that's at x equals 1, and then you would have the function like that. It's a rough sketch. But how do we know that that is the vertical asymptote? So the way we would know that is if we give a value of x to the domain of the function, in this case, that makes the denominator 0. So at x equals 1, f of x equals 1 over 1 minus 1, or 1 over 0. So if you can reduce or make the function for a given value of x, it reduces to some number over 0, then there is a vertical asymptote at that value. There is a vertical asymptote at x equals 1. Okay, because at x equals 1, the value of the function becomes 1 over 0. So if the value of the function becomes some number, some constant over 0 at x equals a, then x equals a is the vertical asymptote. Okay. Now, the holes, they're kind of interesting. You can note there will be holes in the graph for a function. Let's say a function is x squared minus 4 over x minus 2. It's a rational function. And you reduce it to factoring the numerator, you get x plus 2 times x minus 2 divided by x minus 2. And you can see that the restriction here is x cannot be equal to 2 because that would make the denominator 0. That's a restriction for this function. And when you simplify it, this cancels out and it's x plus 2, which is the equation of a line. So if you were to graph this function, you'd actually get the equation of a line, but it has restrictions based on what we had originally. So there will be a hole in this graph at x equals 2. And how do I know that? I know that because if I give the value of x equals 2 in this function, the function becomes 2 squared minus 4 divided by 2 minus 2, which is 4 minus 4 over 2 minus 2, which is 0 over 0. So if at, say, x equals a certain value, f of a becomes 0 over 0, then there is a hole at x equals a. So for this function, if I was doing a rough sketch, let's say this would be my xy axis, and then f of x equals x plus 2, which is a straight line with a slope of 1 and a y-intercept of 2. Then at x equals 2, there would be a hole in the graph here. So there would be a point discontinuity over here This is f of x equals x plus 2, okay? But because of this value of 2 that makes this function 0 over 0, I know there is a hole in the graph at x equals 2. So that would be the break in the graph. So we looked at the scenarios that create a function with a rational function with holes in it. So if you give a value to x that creates a 0 over 0 scenario, that means at that value of x you have a hole in the function and the graph of the function. And if you assign a value of x to the domain of the function and get a number divided by 0, then at that value of x you have a vertical asymptote. We're going to look at horizontal asymptotes. So horizontal asymptotes are interesting because there's 3 scenarios. So if you have a rational function p of x divided by q of x, you have to look at the degree of both the p of x and the q of x. So look at the degree of the function and then decide based on the degree of both the numerator and denominator what the course is. So if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then there is a horizontal asymptote, which is by default always the x-axis. And if the degree of the numerator equals the degree of the denominator, then you would divide the leading coefficients of the numerator and denominator. So I'll give you an example of that, of each of those cases. So the first is if there is, if you have a rational function p of x divided by q of x, and the first scenario is what happens if p of x is greater than, the degree of p of x is greater than, sorry, p of x degree is greater than the degree of q of x. So let's say you have a rational function f of x equals x cubed plus 3x plus 1 divided by x minus 1. The degree of this function, the numerator is 3, and the degree of the denominator is 1. So therefore, no horizontal asymptote in this case. Okay. The second case is when the degree of p of x is less than the degree of q of x. So that's our second scenario. If it is less, then the horizontal asymptote is always the x-axis. So let's say your f of x is like this. It's x plus 2 divided by x to the power 5 plus 4x plus 1. So you can see the degree of the numerator is 1 and the degree of the denominator is 5, and its degree is less than the degree of the numerator is less than the degree of the denominator. Then by default, the horizontal asymptote is always going to be the x-axis, which has the equation y equals 0. Okay, and the third scenario is what if the degree of the numerator is equal to the degree of the denominator. So for example, if you had f of x equals x squared plus 2x plus 1 divided by say 2x squared plus 2x plus 1 divided by x squared plus 3x minus 1. So you can, let's just make this, I'm just creating this as I go along. Let's say it's this, and they both have the same degree, as you can see here. This is degree 2, this is degree 2. Then you take the leading coefficient. The leading coefficients are the coefficients of the term that has the highest degree. So in this case, 2 is the leading coefficient of the numerator and 1 is the leading coefficient of the denominator. Then the horizontal asymptote is going to be, the equation is going to be y equals, you divide 2 divided by 1, which is the horizontal asymptote, which is, there is going to be a horizontal asymptote at y equals 2. Okay, so that's how you would decide if what there is, what the horizontal asymptotes are, and if there is one, when you have a rational function. So there's a summary of that horizontal asymptote. If you look at the textbook definition, you would say if you have a function r of x, which is p of x divided by q of x, and they are represented as ax to the power of m and so on and so forth divided by bx to the power of n and so on and so forth. To find the horizontal asymptote, you have three scenarios. If the m, which is the degree of the numerator, and n, which is the degree of the denominator, if m is less than n, then the horizontal asymptote is always the x-axis, which has the equation y equals 0. If the degrees of the numerator is greater than the denominator, there is no horizontal asymptote. And if the two degrees are the same, then you divide the leading coefficients. So a divided by b, that would be the y equals a divided by b would be the equation of the horizontal asymptote. So let's take this example here. Let's say I gave you a rational function f of x equals x to the power x squared minus 4 divided by x minus 2. This would reduce to x plus 2. And we have seen that before. How does that happen? We would factor out the numerator, which is a difference of squares. So it will be x plus 2 times x minus 2 divided by x minus 2. And you can see, looking at the denominator, there is a restriction, and the restriction is x cannot equal 2 because that would make the denominator 0. And you can, when you simplify it, you get the equation of a line, which is x plus 2. It has a slope of 1 and a y-intercept of 2. But you also find that what happens in this case, the degree of your numerator is greater than the degree of your denominator. So if it is greater, then there is no horizontal asymptote. So we know there is no horizontal asymptote. But what happens if you give a value of 2 to this function? So at f of 2, you get 2 squared minus 4 divided by 2 minus 2. So you get 4 minus 4, which is 0, and 2 minus 2, which is 0. So there is a hole in the graph, at x equals 2. So though you would be graphing this as a line, like this, y equals x plus 2, you would also have to put a hole at the x value of 2 to show that that is a discontinuity. Okay, because notice that at that value you get 0 over 0. Here you have another example, f of x equals x over x squared minus x. You factor out the denominator and you get x times x minus 1. So the restrictions are x cannot be equal to 0 and x cannot be equal to 1, because at those two values the denominator becomes 0. The degree of the numerator is less than the degree of the denominator, so then we have a horizontal asymptote. So if the degree is less, what happens? The horizontal asymptote is the x-axis, which is y equals 0. So we have a horizontal asymptote, which is y equals 0, because the degree of the numerator is less than the degree of the denominator. And we got to see what happens when we give the value of 0 to this function. F at 0, which is a restriction, would be 0 divided by 0 minus 0. So there is a hole at x equals 0, right? What happens when we give the value of 1 to this function? What happens at f at 1? So it'll be 1 divided by 1 times 1 minus 1, which is 0. So it'll be 1 over 0. So there is a vertical asymptote at x equals 1. So in this example, we got a horizontal asymptote, we got a vertical asymptote, as well as a hole in this graph. So when we simplify this function and graph it, we cancel out the x and it reduces to 1 over x minus 1. So it would look like a transformation of the reciprocal function shifted 1 unit to the right, right? So you'll have a function that looks like this. The vertical asymptote is x equals 1. The horizontal asymptote is the x-axis, which is y equals 0. And you're going to have a hole at x equals 0. So this is your origin, by the way. This is your 0, 0. So when you graph the function, there's a hole there, and this has been shifted 1 unit to the right. So that's the vertical asymptote. That's the horizontal asymptote. Okay, so before we graph these kinds of functions, we need to find the restrictions. We need to simplify it and see what the graph works out to. We also need to find out if there are any asymptotes or holes and then graph it. So if a function f of x equals 0 over 0 at an x value of a, then x equals a is a hole in the graph, as we already saw. So I have an example here. Let's say you have a function x plus 1 times x minus 3 divided by x minus 3. If you give the value, if you see the restriction here is that x cannot equal 3. So if you did f of 3, you will see that this works out to 0 over 0. This function, when it's simplified, it reduces to f of x equals x minus 1, which is the graph of an x plus 1, which is a graph of a line with a slope of 1 and a y-intercept of 1, but it will also have a hole at x equals 3. So this is how the graph would look. So that's your function, y equals x plus 1, but you notice that at x equals 3, I have put a hole there. Okay? If for a function you have at a certain value a, the function works out to a number divided by 0, then x equals a is a vertical asymptote. And these are examples of functions that have vertical asymptotes. So here, if you put x equals 2, the function works out to 2 over 0, so you have a vertical asymptote at x equals 2. And that is this graph that I have graphed here, which is the function x divided by x minus 2. Okay. And we also notice that the degree of the numerator is equal to the degree of the denominator. So what happens when the two degrees are the same? If the degree is same, then you divide the leading coefficients, and that's your horizontal asymptote. So for this function that we just saw, right here, you notice that we discovered that there is a vertical asymptote x equals 2, and there is a horizontal asymptote, which is when you divide the leading coefficients, you get y equals 1 over 1, which is 1. So there is a horizontal asymptote at y equals 1. So for this particular example, vertical asymptote at, and vertical asymptote, I'm going to write the equation of it, which is x equals 2, and there's the horizontal asymptotes equation is y equals 1. So when you graph it, you will see that it's a translation of the reciprocal function like this. It's shifted 1 unit up and 2 units to the right, and you get the function this way. We have an example here. Make up two functions such that one with a vertical asymptote at x equals -1, and the second with a vertical asymptote of x equals 2, and graph it. So for the first one, I'm just going to make one up, 1 over x plus 1. There will be a vertical asymptote at x equals -1, because when I put -1 over here, I'll get 1 over 0. So f at -1 equals 1 over 0. So there's a vertical asymptote at that value of x, which is -1. The second function, you want to have a vertical asymptote at x equals 2. So there's so many answers here. I'm just going to make one up. X equals 2. We'll just make this one up because what happens at f of 2, you get 1 over 2 minus 2, which is 0. So therefore, there's a vertical asymptote at x equals 2. And you can easily graph this. I'd like you to do this. You can make a rough sketch of it. This is a reciprocal function that's been shifted 1 unit to the left, and it has a vertical asymptote at x equals -1, and it will have a horizontal asymptote, which is the x-axis, which is y equals 0. Similarly here, horizontal asymptote, which is the x-axis, which is y equals 0. Because you can see the degree of the numerator is 0, the degree of the denominator is 1. So by default, the horizontal asymptote is the x-axis, which has the equation y equals 0. Question B, make up a function with a vertical asymptote at x equals -1 and a hole at x equals 2. So I need to have, so I'm just going to make a function If it has to have a hole at x equals -2, let's say it's x minus 2 here and x minus 2 here, so I get 0 over 0 at x equals 2. And I want to have a vertical asymptote at x equals -1. So let me put an x plus 1 here, so that if I give a value of 1 to this function, this would be a number divided by 0, and I would have a vertical asymptote at x equals -1. Okay, so at f of 2, I get 0 over 0, so therefore hole at x equals 2. And then f at -1 is -1 minus 2, which is -3, divided by, I'm going to get a 0 here, so therefore vertical asymptote at x equals -1. Okay. I want you now to pause the video and try these questions, simplify these rational functions, state their restrictions, and also state if there are any holes or asymptotes, what they are, and then try to draw a rough sketch of these functions. I would also want you to try some more questions here when you're done that, and then go on to the homework. And we'll take up these questions in class. So try these questions over here. First, try these ones. Pause your video here and try these questions. When you're done that, go on to the next set of questions, and then your homework questions.